CS124, hard class. Hopefully you're all ready for it. Yeah, hopefully I'm ready for it too. That's kind of how I feel. So, as is the typical Caltech pattern, this is an introduction to operating systems, and but it's very detailed. You get to do a lot of actual hacking on OSs, which is a really cool part of this class. Unfortunately, this has also backfired because you guys will, well, I'll explain in a moment. There is a hard prerequisite of CS24. So if you have not taken CS24 or you've not passed it, most people pass it, but if that doesn't describe you and you're not a graduate student with equivalent experience, then you'll have to take this course in the future. So that's important to say. Sort of the last half of CS24 is really important. In fact, you'll need it right out of the gate. So project class, yeah, every assignment, substantial programming effort, and we start hard right out of the gate. I'm going to try to get the first assignment out today, and there is a virtual machine image that you can download. We're going to probably end up using last year's VM image. This is how much OS implementation sucks. Last year's VM image is an earlier version of Linux Mint. This year's VM image is one I just built yesterday. And for some reason, the Pintos code works fine on the last VM image, and on this one, it infinite reboot in a loop. So that's not a good way for any OS to behave. Yours will probably do that from time to time, but it shouldn't do that right out of the gate. So it's pretty sad. So we'll probably use last year's VM image. But anyway, let's see. Oh yeah. So yeah, no exams. That's one thing I really love about this class is that it's really easy. You just focus on the assignments and, exam, write a microkernel in 6 hours. Get it done, kids. So, yeah, so that's nice. And we use Pintos, as you probably already know. So, Pintos is Unix-like. It's very Linux-like, I should say specifically. And the one thing that I would mention is that it is implemented in 32 bits. And the build tools and everything else are designed around 32-bit. So, in fact, when you develop on this, you're probably going to want to use the VM image because it's a 32-bit Linux virtual machine. Okay, so if you have a 64-bit Linux VM with 32-bit libraries installed, you'll probably be okay. Many people don't anymore, though. And Macs, you're just SOL. So you'll have to run things in the VM image. So just be aware of that. I'll talk a little bit more about that, and I'm sure that that's, if you have any questions, you can ask on Piazza. We have 2 TAs that are going to be excellent help this term. I couldn't scare up a third, but it's weird because 124 is one of those weird classes where you mainly need help with office hours. Grading is actually surprisingly quick and smooth, but because of how much automation Stanford builds into Pintos, but office hours are obviously where people spend the bulk of their time. Please sign up for the Moodle, CS124 Moodle. The enrollment key, if I did it right, is kernel, and that's where most of the important action is going to happen, except for getting questions answered, because that'll be through Piazza. Also, every assignment has a design doc, and when you submit it on Moodle, everybody should be in teams. One person from the team should submit the design docs on Moodle, and that will be the timestamp for your submission. So that's the thing that needs to happen before the due date. Okay, books, completely optional, prohibitively expensive usually, so irritating to me. Operating System Concepts, the 9th edition, is sort of the high-level, theoretical, parentheses, not very useful information. And it definitely gives you a lot of major themes, but I find it deeply frustrating because OSs are, by their nature, a very nitty-gritty kind of effort. So who needs general concepts? I mean, it's nice to get exposed to them, I suppose, but then you're going to dig down into the gory details really quickly. So there's another book that I really like, Understanding Linux Kernel. I forgot to check if there's a 4th edition yet. Maybe somebody can check on Amazon for me. But this is an amazing book, except for the fact that it's for the Linux 2.6 kernel. And we're way beyond that by now. Do I actually say, yeah, I don't think I say anything about that. But that's the one downside of that book. but it is fantastic for being exposed to a lot of interesting and useful details for a real working production scale operating system. So if you were going to buy just one book for this class, buy that one, Understanding the Linux Kernel. If you're going to buy 0 books, that's cool too. If you have tons of money and want to buy both books, what I'd suggest is buy this book and then give me the money for the other book, because then I can go out to dinner. So anyway, that's all I'll say about the books. Any questions? All right. So assignments, there are 6 assignments, and this is where I'm sad, because of course we're starting at the end of the first week, and so normally I would want to try to cut y'all some slack and cut out an assignment. But every single person that I talked to who took 124 liked every single assignment. But anyway, so I was going to cut out the bootloader, which is actually a really fun project, and the biggest issue people have with it is scope creep, because they get so excited about it. But there's an old school type of computer game called a PC booter. Probably none of you ever dealt with these unless you just really like retro computing. But you'll have a floppy disk, typically in some weird format so that it can't be duplicated, because they had copy protection back then. You put it in the drive and boot the computer, and it goes straight into the game. So fun, but you don't have things like the C standard library. So you can't use printf unless you write printf. You can't use memcopy unless you write memcopy. So that's pretty exciting. So anyway, we're going to include all of them. That's why the first assignment is going out today. And so it should be a pretty, I would say probably a pretty harrowing experience for everyone. So, but anyway, we'll try to make it as painless as possible. The 2-week assignments are obviously worth twice the points of the 1-week assignments. So, and just as a hint, also, I don't mention it on this page, but you guys get 6 late tokens. It may still not be enough, but you get 6 late tokens. And what I would recommend is try not to use them at all for the first half of the class, and save them for these guys. Because virtual memory and the file system are a little bit brutal. And so you'd want to try to save them for these. So that's, if you're already burning like 3 of your 6 late tokens, by the way, that's on a per team basis. It's not like the team gets 18 tokens. But if you're burning all your tokens on the first 1 or 2 assignments, then you probably either should take the class in the future, get a little bit more programming maturity, or you were too ambitious with your goals. It's probably one of those 2 things. So, okay, any questions about that? It is a really fun sequence of assignments, so I hope you all have a lot of fun with it. Okay, yeah, so the assignments are hard. Nobody makes any bones about that. We require groups of 2 to 3 students. I already mentioned that in the opening email, which only registered students got. So if you didn't register, then this is important. So it's not that you're not able to do it. In fact, there have been 2 people who completed this course by themselves before we started requiring it. But what we always noticed is that they had more difficulty debugging things because they didn't have another person to bounce things off of. You may have even heard of rubber duck debugging. Anybody heard of rubber duck debugging? So yeah, if you've got a rubber duck, that could be one of your teammates. But not in this class. So it's really actually helpful when you have complex systems to talk through issues with someone. Okay, and also I mentioned dropping in the initial email. You need to probably be with a team that has equal levels of commitment to the course. And I don't like to mention the S word, but a lot of times teams will, some teams will make a suicide pact kind of thing, where like if one teammate decides to drop, then usually all the teammates decide to drop. Or if one teammate decides to piff, the rest decide to piff. It can be challenging. If one teammate decides to piff, then they may not want to work as hard as the other teammates who are on grades. And so you just have to think about all these things up front so that you don't get in a situation where you make a permanent enemy before you even graduate. That would be really bad. So, yeah, and I'm always happy to adjust teams. In fact, this is one of the things, I think I mentioned it in the Moodle write-up, but I haven't copied that over to the current year's course. People problems should always be handled early when they're small. This may be one of the hardest projects you ever do with other people. And If you have people issues, you need to deal with them when they're small, not sit and stew on them until they're monstrously huge, and then like I have to intervene or something like that. So it happens. I will, but we'd really like to try to avoid those things up front. This is all part of real life programming. I mean, you'll run into people issues all the time in software teams, so it's just something to learn to deal with. Okay, we'll be using Git. Codebase will be published on a CS cluster repository, so at least one of your teammates will need to have CS cluster access. When I say CS, of course, CS and CMS are equivalent. A lot of people get confused because they think, I sent Donnie at CS an email, and so he didn't get it because it's Donnie at CMS. They all go together. So CS cluster, CMS, same thing. All right, so you have two options. One is that I can create a Git repository for you. I don't prefer this option, but it is an option. The other option is that you can create a Git repository on GitHub or Bitbucket, or GitLab now, I think, is starting to become more popular. So if you do this, make sure it's private. If it's a service that requires paying for private repositories, see if they have an educational option. Most of them do. So, boom, there you go. And then you would grant access to me and the TAs. And they all have definitely GitHub, probably Bitbucket, probably GitLab. So just give us those, and we'll be able to access your work. It can just be read-only access. That's fine. We're not gonna fix your work. That's your job. So, all right, and then yeah, that's where you'll push your code, and then just give us the commit hash in your design doc, and then we'll know what version to pull. All right, any questions about this? Okay, that's easy enough. Obviously, since we're working in teams, the collaboration policy is at the team level, not at the individual level. I don't believe we've ever had problems with CS 124, which is great because teams definitely alleviate a lot of the challenges that students face in needing to collaborate closely on challenging projects. So these are areas where you can share between teams, and I strongly encourage it. Design and implementation ideas. Sometimes these are shared on Piazza, sometimes they're shared in the lab on whiteboards and so forth, so that's totally cool. Not code, not pseudocode. Pitfalls you encountered, always fun. Like, I'm going to be bugging my TAs and saying, hey, I ran the original code against the new VM, and it is an infinite reboot loop. See if Henry has any ideas, or see if Rudy has any ideas. And then help with setup and debugging. One of the number one issues, like, we'll run into this all the time. GDB is totally your friend, and the way that Pintos is set up, you can connect to the emulator with GDB and debug your OS as it's thrashing around. So that's really awesome. We strongly encourage, and I would even go so far as to say require you to do that before we start helping people, because a lot of times it immediately reveals the issue that people are dealing with. Okay, Pintos has been around, if you think about it, 16 years old. This is one of the things that makes me sad, but we don't have time to fix it, which is that it's 32-bit, relies on BIOS. Now everybody, unless, for whatever reason you don't want to, is using 64-bit, and many people are using UEFI as opposed to BIOS. So, suspension of disbelief, that's part of the learning experience. But anyway, since it has been around so long, there are solution implementations online. Please don't look at them. But you are allowed to look at other sources. In fact, I encourage it. If you want to look at the Linux source, do it. That's awesome. If you want to look at the OS Dev website, there's like OS Dev Wiki. If you just type that into Google, or Bing, I guess, then it'll show up. I don't know if Bing will make it show up. But anyway, again, there's lots of useful information out there. And like I say here, the whole goal is don't copy code. What we want, though, is for you to understand it. A lot of these things, since you're working with hardware, are incredibly baroque. Okay? Like, I don't know if anybody here knows this, but for whatever dumb reason, one of the address lines on the Intel, PC mainboards is routed through the keyboard controller. It's a decision they made back in the XT-AT days when they were pushing up against the 1 megabyte memory limit. So to enable your full memory address range, you have to talk to the keyboard. That seems crazy. So there's all kinds of insane things like that you see. And so a lot of times you need to go to these resources and look at stuff. Now, I spell out as much as I can in the assignment write-ups, but I encourage this. And there's a section in the design documents with citations, so you can say, hey, here's a useful reference, so that other people can benefit from that in the future. Okay, any questions about this? If you have any questions in the future, please talk to me. That's an important aspect of the honor code. You have to talk to the teacher to figure out if I'm confusing or if a particular case you're not sure about. Come talk to me. I'd be happy to resolve that. Okay. And there may even be things here that I haven't talked about that I wouldn't mind, but I don't want to spend 40 minutes talking about the collab policy. I want to talk about OSs. So just come talk to me if you have any questions. Okay, due date. So there are late penalties in this class. It's just like CS121 and 24 and everything else. So 10%, 30%, 60%, sad. And so you have more late tokens in this class. 6 is usually enough. But still, a lot of teams use all 6. And so I'm just going to put that out there. Really try to save them for the end of the course. That's what I would strongly encourage you to do, is save them for the end of the course as much as you possibly can. And don't let scope creep nail you. That's the number. We'll talk about that more when we get to the PC booter. Okay, also, this first term, people are going to be flying to interviews, blah, blah, blah. So if you have any situations like that, just let me know. It's obviously more different and interesting because if one teammate is disappearing, then obviously you're a person down. So I'll have to figure out those kinds of issues. But I usually just close my eyes and make a guess, and then that's what we do. So yeah, like I said, contact me if you have any situations like that. Okay, any questions? All right. I was mentioning Pintos is implemented on 32-bit. It was designed. I wouldn't say it was designed before UEFI existed, but it probably was. EFI may have existed. Because I'm pretty sure the, what is it? There was a particular Intel 64-bit processor that was designed that motivated the need of EFI. And it's the Itanium, that's right. It was a very interesting processor, but unfortunately has not caught on. So anyway, since we have this interesting constraint of 32-bit Linux, we're going to basically apply this across the board. Everything will be 32-bit Linux. I built a Mint image because Mint is kind of lightweight, and it's Ubuntu, so if you're familiar with Ubuntu, then that'll be fine. But I would at least encourage you to test on it. Yeah, and it would even be a good idea to develop on it, which is why all the development tools are on the VM image. Make sure you're committing and pushing regularly. Invariably, like twice or 3 times a year, I get my laptop exploded or accidentally fell under a truck that was driving by, and I lost all my work. Like, that is very sad. So just make sure that you're pushing it to the shared repository regularly so you don't lose any work if you have a failure like that. The other thing that I would tell you, again, OSs suck. You have 2 emulators that you'll get to test with. And this is Pintos really specifically. And it may be that tests fail on one and pass on the other. Well, guess what? I let you tell me which emulator to test with. It may also be that tests fail on one teammate's laptop or computer and they succeed on another computer. That's the fun of OS implementation. Now, this is not Microsoft, this is not Red Hat, this is not, Apple. I do not expect you to get your OS working on all platforms. That would be cool, but that's not really realistic for 10 weeks. So, if you run into these kinds of situations where tests are failing on one laptop and not on another, talk to me, because in all likelihood we'll just say submit it. If it runs on a TA's laptop, you're fine. So, there's even weirder vagaries that we run into. So, yay! What a crappy topic for anyone to study. Why are we doing this? I don't know. Yeah. So the other thing that I wanted to mention is that we do focus on Unix a lot. You'll see me sometimes write Starnix, and that includes like OS X because that's actually a BSD variant. Linux is also not Unix technically, but we kind of mean all of those things. So Also, the other thing about this is that there's actually really cool things in other OSs besides, like, Linux isn't the coolest OS out there, bar none. It does some cool things. So does Windows, like especially after Windows 7. And of course, Mac OS is really interesting as well because its kernel derives from the Mach microkernel, which is very interesting. So there's a lot of interesting details across all OSs, and I'll try to bring those out. But I don't want you to assume anything because we've focused so much on Linux in the assignments. Okay, any questions about any of this? Any of the stuff we've talked about? Okay, so that's the preamble. Now we'll get to the amble. What is an operating system? You know, like what would you say is a good general definition of an OS? What should it provide? What are some of the most basic requirements of what an OS provides? Yeah. Memory access and paging is a specific instance of a more general topic. What about disk access? That's also another one. What about CPU access? That's another one. So these are all instances of what? Yeah.
Letting programs talk to the hardware.
Yeah, that's a great way of putting it. We got to let programs talk to the hardware somehow. Now, what are complicating factors in that? Like, what makes it complicated that we have programs that want to talk to the hardware? Yeah.
How do you arrange who gets to talk to hardware when? How do you have a program know where is the hardware, how it's supposed to talk to it, etc.?
Yeah, that just captured a lot of important details. Yeah.
You also want to have it work on different hardwares as well.
That's also extremely important. So you guys, hopefully this is starting to like provoke some thoughts in your brains, because like these are the challenges that an OS has to solve. I have to figure out how to allow programs to access hardware. I have to allow multiple programs to access the same hardware without allowing it to become a giant mess, right? So that's first thing. I have to manage resources on behalf of programs. Now the second part of it is that hardware sucks, and I mean I already mentioned this, you know, with the early Intel x86 systems routing the A20 address line through the keyboard controller. It's like, who thought of that? Well, at the time, you didn't have big integrated circuits where you could stuff everything on there and have this really large integrated system on a chip. You had a bunch of discrete chips, and sometimes it would really suck to put that one extra chip on there. And so instead, you try to figure out how to reuse functionality from other circuits. So you end up with junk like that you have to deal with. And so the OS also has a second responsibility of trying to find a way for programs to talk to hardware in coherent ways that abstract all the nastiness of hardware. That's the other major aspect of what an OS has to do. So most generally, we say an OS provides application with standardized interface, and we also have to manage the allocation and sharing of resources. Okay? CPU is one of the biggest examples of a resource. A lot of times people don't think about that until they get to writing an OS. And then they realize, oh, the CPU is the most important resource to manage. Okay, so there's a lot of variations. How we architect the OS, what kinds of devices the OS runs on, and facility services guarantees that the OS provides. Like I mentioned before, I mentioned this actually rather frequently, because real-time scheduling is cool. But then you have the question of, if I miss a deadline, is the system now in a failure mode, or does it just mean the cat video stuttered? You know, it's like you can clearly see that there's different levels of expectation. If my anti-lock braking system doesn't run 1/20th of a second, every 1/20th of a second, then maybe my car skids out of control and I fly off the cliff and die in a horrible fiery death, right? But if my cat video just doesn't play right, then I don't really care so much. So that's one example of a level of service guarantee that an OS may or may not provide. Okay? Now, I want to mention there's a whole bunch of stuff I'm not talking about because this lecture is basically the minimal that we need for this week to get the command shell running. Okay? So last year's lectures are available. There's a lot of I find it fascinating discussion. That's, I guess, why I'm teaching this class. But anyway, if you want to see a lot of the background detail, then you should definitely go and watch those lectures because you'll get a much greater development. And in fact, one of my favorite aspects is that you get the historical background of why computers are the way that they are now and why OSs have the features they have. It developed in a very straightforward manner given the available resources, computing resources that, for example, universities and companies had. And so I find it really interesting. And it's important to know your context, so you know whether something's been invented before. Okay, but I'm going to look at file systems because that's very important for the first assignment. We have a lot of different storage media. If I asked you, like, what does your laptop, a bunch of you are staring at laptops right now, what storage media did your laptop support? Anyone? I don't want the same three people to always answer. So everybody has laptops. Yeah.
HDD, SSD, RAM.
Yeah, sure. You have a hard disk, spinning magnetic rust bucket, solid state drive. You said RAM. But let's talk about storage media in particular. So let's talk about persistent storage. What else? Yeah.
Volatile storage.
Volatile. Well, let's not talk about volatile. Let's talk about persistent. So anybody got a USB port? What does that allow? Yeah.
You can plug in an optical drive into that.
That's a great example, an optical drive. Optical drives turn out to use a different format than any of the other things we've mentioned so far. Okay. You could have a flash drive, of course. You could probably come up with other ones as well. You could say, well, what about Dropbox? And that would be a good example. Okay. So you have a whole bunch of different storage media. If we just looked at hard disks, we could even get more crazy because look at, I don't know if anybody here has ever even seen a parallel ATA drive, let alone has one that they use, because serial ATA has entirely supplanted it. But then you have SCSI, which again is another older one. I think now we have what? I can't remember. There's SAS, but I don't remember. There's another one that people use. And then, of course, you have USB disks. You have other ones like that. These hardware interfaces all require different interactions. Like, you can't just talk the same language to them all. They all have their own language. Different size hard disks. Thankfully, not so much of an issue anymore. But let me show you a glimpse into the world that I grew up in. It used to be that we had cylinder head sector addressing. Remember the spinning disks? They have platters, and then platters are divided into tracks. All the tracks at a certain distance from the center spindle are in the same cylinder. So you would say, I want this cylinder, I want to pick this head, and I want this sector off of that. That was sufficient to identify a sector on the disk. Started failing badly for two reasons. One is, as disks grew larger, we didn't have enough bits in these different values to say, I want cylinder, whatever, 1 million or 10 million. Okay? That was a big problem. The second thing is this stopped reflecting reality because modern disks have zones, and zones closer to the edge of the platter have more sectors around them than zones on the inside. Yick, right? So this got changed a couple times. And then we finally settled on logical block addressing, where, hey, let's just say that block 0 is the first block on the device. Block 1 is the second block. And then we'll just let the device take care of all the details. This actually works with solid state, and it works with spinning magnetic disks. This is really nice, so this is what we do now. Okay? But you can see that talking to these things can be really hideous. Also, you have different kinds of devices with different kinds of maintenance. Does anybody here actually have a magnetic disk in any of the computers you use regularly? Like one person? What OS do you run?
It was Windows 7.
Okay. Did you ever have to think about defragmenting that drive? Oh, so irritating. You say, oh, my computer's running really slowly. Okay, delete all my well, first reboot, right? And then second was delete all your cookies. And the third one was defragment your disk. What a giant pain in the ass. Okay? But you have to think about that, because if you have a large file and the logical and physical layouts aren't the same, then you're going to have really slow sequential access. And so you have to think about that. Solid-state drives don't care about fragmentation. But they care about something else, which is that you can only write to each memory cell once, and then you have to erase it, but you can't erase individual cells. You have to erase them in big erase blocks. not only that, but erase blocks wear out. The more cycles I put them through, the closer they get to their end of life where they can stop, they can't hold data anymore. So basically, something somewhere has to think about how to manage the wear of this device and make sure that it can periodically erase things to free up space for new writes. Okay? Solid-state drives, in fact, the way I talk about this a lot in CS 122, so if you have taken that class or intend to, you'll get more of this. Magnetic disks are really great for in-place writes. If I have a sector, it's already got some data, I want to write more data to it. Like hard disks love that. They're just really great at that. Solid-state drives hate that kind of access pattern. Solid-state drives love log-based writes. And so there's actually a lecture toward the end of this class where I talk about log-based file systems for solid-state drives. Really interesting topic. But you can imagine the file system design could be completely different for these two kinds of devices. Okay? And then you have formats. I don't even have like some of the formats that we use now. Okay? We used ext4 for a long time, but now BetterFS is, or ButterFS, whatever you like. I like butter, so. Anyway, but you have BetterFS for a lot of Linux installations now. Any other file systems that you may... In fact, I think Apple updated their file system as well from HPFS, right? They have a new one that's really clever. So you can read about that. It's absolutely fascinating. But anyway, all these different formats, and you plug in a USB drive, and that's going to be FAT32, and then you're talking to your hard disk, which is NTFS, and you're talking to your optical drive, which is another... I say ISO 9660, but there's actually a new version of the standard used. Maybe this would be for old CD-ROMs. So, you have to have something manage all of that complexity. So this is what Unix does. This is the beauty of Unix. Windows does something similar. Basically, it just defines an abstraction. Open, close, read, write, and so forth. And everything is lumped into a single virtual file system, so that everything is available on some path from the root. You can mount devices in the path, in the file system, so you can have your CD-ROM appear, you can have your hard disk appear, you can have different partitions of your hard disk appear, all of that stuff. So, makes it very straightforward to access everything in a nice, clean abstraction. Okay? Sockets work this way too, and pipes work this way. It's crazy. It's really cool. They designed everything to use this clean, simple abstraction to hide and obscure all of the nastiness of the hardware, okay, including resource sharing. Okay, any questions about this? These are some things you'll get to play with this week. So so the only real API difference at this level is how do I open a socket or how do I open a pipe. So for example, you would call pipe to get a pipe. You can call open or socket to open a socket, and so forth. So there's that's basically the only place things change. Okay, that's the first part. So you can see how abstractions clean things up. Another issue, multiple processes can access the same file. Scenario that hopefully never any of you will have to actually think about carefully. Someone does sometimes, so thankfully they handle it in a certain way. Process A opens a file, intending to read and write it, and then another process comes along while A is still using the file and deletes it. So what should happen? Let me rephrase this. Let's say that it attempts to delete it. What should happen? Yeah.
Hopefully be a flag saying don't do that.
There could be a return value that says don't do that. Sorry, you can't delete it. Somebody else is using the file. That's the approach that Windows chooses most of the time. You open a file, it locks it so that other people can't manipulate it. What's another option? You have a guess?
I guess what you can do is have it set for deletion, and then process A can decide to whether it should still be saved or deleted.
That's a very interesting idea. So we could sort of queue up the deletion, and then maybe give a veto power. That would be another option. Now here's the thing about all of this. This is a choice that the OS implementer makes. So this is convention, this is not theory, and this is not proofs or anything like that. You have to choose a way of handling these kinds of scenarios. Unix happened to pick a way. Windows picked a way. Your way would be perfectly valid, but it's not precisely either one of those. So yeah, you have options, but the OS is the one in charge, so it's got to make the choice. It's got to figure out what to do in these situations. So basically the OS is the thing that takes care of this. In Unix, just so that you know, process B's deletion attempt is allowed to succeed, unless there's some kind of mandatory lock imposed on the file. And so basically what happens is the OS will remove the path to the file. No one can open it subsequent to the file being deleted. But the file data, so you can think of this, the directory entry pointing to the file data and the file data itself are separate. And the directory entry is removed. When the process terminates, then the file data is also removed. That's how Unix solves it. Okay? That's one way of doing it. It's not the right way, it's just a way of doing it. All right, any questions? So there's some fun, exciting things for you to think about. Let's see. So for the sake of time, yeah, we're going to hopefully finish just under the wire. Again, this is a section of the lectures, the first week of lectures that I cut out, but I wanted to show you a few details. This is a nice picture of all the things that generally could be in an operating system. They aren't always. Think about, for example, like a graphical user interface. That's the GUI on the third level, or the second level, I guess. What if you have an embedded system without a graphical user interface? Well, then you won't have a GUI. Okay, that's fine. But basically, the interesting aspects of this is you'll notice that the OS may be factored into multiple parts. A lot of times we have applications which are not part of the kernel proper, but they're still a necessary and essential part of the OS. That's why I'm excited that you guys get to write a command shell, because a command shell is a really important part of an operating system. But it does not need to be in the kernel, and it should not be in the kernel. You'll get to think about why in part of assignment 1. Okay? Same thing with a GUI. You probably don't want a graphical user interface in the kernel if you're at all familiar with how many bugs graphical user interfaces can have. Okay? Now you can see in here the OS has a lot of different things that it has to manage. Program execution, this is where we talk about managing the CPU as a resource, scheduling, what kinds of scheduling guarantees do we provide, resource allocation, who gets access to what, enforcing the rules, file systems, I/O services, we've talked about that, communication, so we have in between processes, from one process to another computer, you have all of these kinds of things that we might have in communication. Error detection. Your printer is out of paper. That is an example of an error that the OS should communicate. I get that one a lot, actually. And then protection and security is a really interesting one. We're going to spend some time talking about that. The OS itself has this gateway of system calls. You all will get to implement system calls in Lab 4. Yeah. One-based indexing, Lab 4. So, sorry, teaching OSs and databases in the same term is hard on my brain. So, anyway, the system calls cannot trust anything from applications. But they're executed by the OS, and the OS can do anything. So the OS has to be very distrusting so that the system can't be brought down by an errant or malicious application. Okay, so lots of interesting stuff. If you want more detail on that, watch the lecture slides. But I do want to talk about protection and security, because there's two main features that we really require to implement protection and security properly. One is multiple operating modes. We already talked about this in 24. At the very minimum, I need user mode and kernel mode. Okay? Most computer systems nowadays have numerous operating modes. Intel has 4. ARM processors have 7. Okay? So there's a lot of operating modes. And in fact, Intel processors don't really have 4 because they also go down below ring 0. They have system management and other crazy stuff that you don't even really want to know about. Just close your eyes and use your computer and don't think about all the security issues that really exist. Anyway, yeah, that cheery thought. Let's see. So what is the kernel? We all use this term, kernel. The kernel is just the part of the OS that runs in kernel mode. Can't really get a simpler definition than that. So you will have other parts of the OS, but they'll live outside the kernel. And you might think, well, it'd be nice to keep this kernel as small as possible. We'll talk about some of those things next week. Okay, any questions about this? So we need multiple operating modes to provide some security. Second thing we need is virtual memory. This is what was mentioned earlier. We need a way of isolating process address spaces. We need a way of saying this process cannot access information outside of a specific set of memory pages. Okay? This obviously should be only manipulable through the kernel. Okay? So yeah, we're going to spend a lot of time talking about that in the future. But if you have those two things, access modes, operating modes on the processor and virtual memory, you can build a reasonably okay OS. Now there's one other feature you need. Does anybody know what it might be? Yeah.
Context switching.
Context switching, so why would you need context switching? Like what is it about context switching that you think that we want?
For programs to run without any concern of another program that they might
Sure.
be on at the same time.
Yeah, so that's a good consideration. We can build it if we have these features, right? Hopefully you all at least got an idea. You'll get much more of an idea this year because you'll get to manipulate the page table for the processor. So that's part of the context switch. But here's another issue. What if a program never decides to yield? Never performs any I/O? When is it going to context switch? Any guesses? Depends on the OS, right? Windows up to Windows 95 would let the process hang out on the processor as long as it wants until it yields, blocks, or terminates. Bad idea, because programs misbehave sometimes. I've written a few of those.
Sometimes.
Yes, sometimes. Sometimes they run very quickly and don't hit any of their bugs and then terminate. So, but yeah, so the third thing that you really need to build a fully sophisticated modern operating system is a timer that you can use to fire interrupts and kick a process off the processor. So if you think about it, if you want to have a nice modern preemptive operating system, you need operating modes, virtual memory abstraction, and a timer that's configurable only by the kernel. Those are your ingredients. Then you can build a good OS. That's also why DOS sucked so much at the beginning. Microsoft didn't have good hardware to work with. There was no operating modes. There was just the one operating mode. Okay, let's see. So once you have virtual memory, then you can lay out an address space however you choose. Now, you may notice that this is different than the CS24 address space because this is 32-bit Linux. This is what Pintos uses as well because it makes linking really easy. You link it on Linux, you run it in Pintos. Okay, so processes have identical memory layouts and so forth. Now you'll notice that above 3 gigs, you start getting into stuff the kernel cares about. Well, this is curious. And so you could imagine you don't want programs accessing that part of memory. And so you can control the access privileges of address ranges. And so you can restrict that to say only kernel mode code can access that address range. It's still in the process's address space. The process can't actually access it. You know, ignoring things like Meltdown and Spectre, of course. But, you know, barring, cache timing exploits, you can't access that memory without causing a fault that would cause the OS to intervene and say you're being very naughty. Okay? So we have kernel space and we have user space. User space is only accessible by user mode code. I'm sorry. That's an incorrect statement. User space can be accessed by the kernel as well, but it's the part that user mode code is restricted to. And kernel space is accessible only by the kernel. So I kind of got that backwards, but hopefully you understand what I mean. Kernel space accessible only by the kernel. User space accessible by the kernel or the program. Okay? Questions about that? All right? And so the OS manages details for various processes. Okay. Yeah, we don't allow processes to do that directly. So let me just show you the last little part of this. You run a program on most modern operating systems, and certain things happen for you automatically. You get standard input, and standard output, and standard error. Okay? And you may have asked the question, or maybe you never considered it, where do those things get set up and how are they managed? Okay? Another interesting question is, what are they actually? Like when you're running programs from the command line, what can they be? It could be the console. It could be other things too as well. Like I can redirect input from a file into my program to make it do things in an automated manner. Okay? So you have interesting details like this. You can redirect to and from disk files. Even more wildly, you can do this with other processes. So you can have one process's output go to another process as its input. And now you get one process generating results that drive another process to do something. Okay? So this is really cool. And again, it all comes down to our simple file I/O abstraction that's provided by the operating system. You have read, and you have write. Okay? We attempt to read or write some number of bytes specified by a file descriptor. Okay? The actual number of bytes read or written is returned by the function, because if you're reading a socket and saying I want 1,000,000 bytes, it may return after giving you 35 bytes, because you don't want to wait for 1,000,000 bytes, or maybe there aren't 1,000,000 bytes ever going to show up. Okay? EOF is indicated by 0. Okay? And so this is a request that's a system call to the kernel. The kernel has to do this for the program. Okay? And it also happens to be a perfect time to context switch to another process. Remember? Block, yield, terminate. Those are the 3 times that we'd love to context switch. Okay. So, FileDes is a file descriptor. And just to try to give you the punchline, try to get this all in, the file descriptor is just an index into an array of file entries that are managed on behalf of the process by the kernel. And each one points to a struct that holds details about the open file. So, for example, we need to know the offset in the file if it happens to be a block device that we can see. Okay? So that's important. So yeah, FileDes is just an index. So you can imagine file descriptors have to start at 0. Okay? So processes have these data structures, but they're not allowed to manipulate them. And then the individual file structures, remember that like all of this from here over is in the kernel on behalf of the process. So the file object points to a more general thing that describes the open file itself. And this is where we can actually support a whole bunch of different kinds of files on kinds of devices. So you'll have that file ops pointer, and again, this is exemplary. It's every OS does it slightly differently, but they all follow this pattern. You have a pointer to a struct with function pointers in it. Yay, right? And so you'll have functions like this. Read from a file, and then the other arguments are passed straight through, so that you can implement file I/O on a whole bunch of different kinds of things just by doing the indirect operation. You take F, let's see, so first of all we look up the pointer to the file object in the file descriptor table. Then we use that to go to the file ops thing and invoke the appropriate function for that type of device and file. Everybody got that? So this is what your kernel is doing to implement the abstraction that you get to enjoy as a program. Okay? It's really neat. I don't think you get to do this in Pintos because Pintos only supports file system files. Okay, so yeah, we can talk about that. Let's see, the last thing that I want to talk about, just because we're almost out of time, is file descriptor 0 is almost always standard input, 1 is almost always standard output, and 2 is almost always standard error. Those are the file descriptors that are always set up for you. You should use the definitions from the UNIX standard header. I won't spend any time talking about that. But yeah, programs generally don't care about redirection. But the command shell does a lot. It needs to analyze something like this, where I'm redirecting log file in, redirecting the output to another file. And so we need to be able to change the file descriptor. Okay? So, yeah, unfortunately I don't have enough time to go through all of this, but you can look at this for the details. A lot of this you may already know from some of your own programming experiences. But the command shell has to set up the redirection. And so how does it do that? Well, I'm going to skip over this. That's important to understand. And this as well. But the lots of pictures. I think you guys will find it really easy to understand. These are the punchline. There's 2 system calls, dupe and dupe2, which allow you to manipulate file descriptors. Or really what it is you're asking the kernel to do it for you. And that's very important for how a command shell works. Okay? So let me see. Dupe, you won't care about. Dupe 2 is the interesting one. Duplicate a file descriptor of a file you've already opened into an existing file descriptor. Like replace standard out, replace standard in. Okay? So you'll have to do stuff like this for this assignment. Now, I talk a little bit about the details. It's all very straightforward, but looking at this example, you can see we have to open the file, we get a file descriptor back, we dupe to it into standard in, and then we close our input file descriptor, leaves the standard in descriptor open. We have to open the output.txt to redirect output, we dupe to it into the standard out position, and then we close our output file descriptor. So this is the kind of thing command shells have to do I/O redirection. Piping is a more complicated version, but it does the same thing, where you just take file descriptors and you duplicate them into standard in and standard out, and then let the whole thing run. Okay, any questions? All right, I know you probably were just overwhelmed by that whirlwind tour, but get on Piazza, ask questions, ask TAs questions, ask me questions. We have to get out of here because there's another class. So anyway, I'll see you on Monday if I don't die over the